At the end of the previous video, I mentioned that one of the important uses of the inverse Fourier transform is in the context of data analysis and signal processing. And the idea is to implement signal processing techniques in the frequency domain and then use the inverse Fourier transform to get back to the time domain. So I also mentioned that I'm going to discuss these topics in more detail in a later section of this course, as well as in my signal processing course. But I thought it would be interesting to already introduce the idea here. So here is the idea. You compute the Fourier transform of a signal, change the amplitudes or the phase values in the frequency domain, and then compute the inverse Fourier transform to get back to the time domain. This procedure is useful only when there are clearly spectrally separable components in the signal. Let me show you an example of using the inverse Fourier transform for bandstop filtering in MATLAB. So here I create a signal. It's just the sum of two sine waves at 4 Hz and at 10 Hz. Here I compute the Fourier transform, nothing new, nothing new. And then here I'm going to compute the inverse Fourier transform and then make some plots. So first let me show you what the original plot looks like. So I'm going to run this code, and I don't yet care about this stuff. I just want to show you what the original signal looks like. And I'll also show you the original amplitude spectrum. All right, so here we have our signal. It's a combination of a a 4 Hz and a 10 Hz sine wave. So there's two sine waves summed on top of each other. And that you see perfectly accurately reconstructed in the amplitude spectrum here in this plot. Now, what I want to do is eliminate the 10 Hz frequency component from this spectrum so that we get a pure sine wave at 4 Hz. That's going to be the goal. And the mechanism, the way that I'm going to do that, is by taking the Fourier coefficients from the forward Fourier transform. And then I'm going to identify the frequency index corresponding to 10 Hz, so that's going to be this component here. And then I'm going to set that Fourier coefficient to be 0. So now that I've modulated the Fourier coefficients, then I'm going to do a reconstruction using the inverse Fourier transform. And now I'm not using the original Fourier coefficients, but the modulated Fourier coefficients with the coefficient corresponding to the 10 Hz component set to 0. And then we're going to plot that and see what that looks like. All right, so now I'm going to run this entire cell, and we can take a look. So here's the original signal. This is the amplitude spectrum of the original signal. And now here is the bandstop filtered signal. So you might be a little bit confused and perhaps a little bit disappointed because I said that our goal was to reconstruct exactly the 4 Hz component without the 10 Hz component. But when you look at this, this is clearly not a pure sine wave. In fact, it looks an awful lot like this original signal, but these faster sine waves are dampened, so they're a little bit smaller in amplitude compared to what they are here. I encourage you to pause the video and see if you can figure out what went wrong here, what's wrong in the code, and why we still have a 10 Hz component here. So it turns out that what went wrong here is that I didn't account for the fact that the amplitudes of this 10 Hz component is split between the positive frequencies and the negative frequencies. So in fact, what I've done here is zero out the positive frequency, but I did not zero out the negative frequency, the corresponding negative frequency for 10 Hz. So that means that I only actually attenuated the 10 Hz signal. I got rid of half of its amplitude. Half of its amplitude was still in the negative frequency. So let me do that. Let me get rid of the corresponding negative frequency. So that's going to be F coefs modulated. And now I want so I want to go from the end, so the negative frequency is going to be from the end minus frec IDX. And then we have to add this +2 here. So this +2 is actually just a MATLAB indexing. Normally it would be a +1 for typical indexing. However, you also have to account for the DC component. So the DC component is the first element in the positive frequencies, but remember that the negative frequencies don't have a 0 Hertz component. So therefore, we have to add an additional offset to the negative frequencies going backwards to account for this DC component here. I realize that's a little bit confusing, but this is just something about programming and indexing. This is not really about the Fourier transform. The important thing about the Fourier transform is that I'm also setting to 0 the Fourier coefficient corresponding to minus 10 Hertz. Okay, and now I'm going to run this whole cell again. And now you see we don't see any 10 Hertz component in the reconstructed signal. There's only a 4 Hertz component. Now from this example, you can see why this procedure is appropriate only for signals that have clearly spectrally separable components. If these two signals, these two components of the signal overlapped in the frequency domain, then simply removing some frequencies is not going to isolate one part of the signal. Now, one important word of warning. This procedure, where I just zeroed out one Fourier coefficient, can introduce artifacts in the time domain signal. So typically, you would not want to just set some Fourier coefficients exactly to 0. Typically, you would want to have some kind of gentle slope instead of a hard edge. I'll show why that's the case in the section about the effects of non-stationarities, and in my course on signal processing, I talk a lot more about optimal design and appropriate design of low-pass filters and high-pass filters, band-stop filters, and band-pass filters. In this case, this very hard edge filter happens to work really well because the signal contains only pure sine waves. In this video, I showed you an application of using the inverse Fourier transform to suppress one spectral feature of a signal while leaving another spectral feature untouched. This shows the usefulness of the inverse Fourier transform for signal processing applications.